Okay, hi everyone, welcome back to this live stream on Windows Server 2003. So I just want to share my screen. Okay, subnetting a network. If an organization is large and has lots of computers, or if its computers are geographically dispersed, it makes good sense to divide its colossal network into smaller ones connected by routers. These smaller nets are called subnets. The benefits to using subnets include the following: reduced network traffic. We all appreciate less traffic of any kind, and so do the networks. Without routers, packet traffic could choke the entire network. Most traffic will stay on the local network. Only packets destined for the other networks will pass through the router and over to another subnet. This traffic reduction also improves overall performance. Simplified management. It's easier to identify and isolate network problems in a group of smaller networks connected together than within one gigantic one. The original designers of the IP protocol envisioned a small internet with only mere tens of networks and hundreds of hosts. Their addressing scheme used a network address for each physical network. As you can imagine, this scheme and the unforeseen growth of the internet created a few problems. To name one, a single network address can be used to refer to multiple physical networks. An organization can request individual network addresses for each one of its physical networks. If these requests were granted, then there wouldn't be enough address to go around. Another problem relates to routers. If each router on the internet needed to know about every physical network, routing tables would be impossibly huge. There would be an overwhelming amount of administrative overhead to maintain those tables, and the resulting physical overhead on the routers would be massive. CPU cycles, memory, disk space, and so on. Because routers exchange routing information with each other, an additional related consequence is that a traffic overabundance of the network traffic would result. Although there's more than one way to approach this problem, the principal solution is one that will be covered in this book: subnetting. As you might guess, subnetting is the process of carving a single IP network into smaller logical subnetworks. The trick is achieved by subdividing the host portion of an IP address to create something called a subnet address. The actual subdivision is accomplished through the use of a subnet mask. More on that later. In the following sections, you will see exactly how to calculate and apply subnetting. Implementing subnetting. Before you can implement subnetting, you need to determine your current requirements and plan on how best to implement your subnet scheme. Follow these guidelines. Determine the number of required network IDs, one for each subnet, one for each WAN connection. Determine the number of required host IDs per subnet, one for each TCP/IP device, including computers, network printers, and router interfaces. Based on these two data points, create the following: one subnet mask for your entire network, a unique subnet ID for each physical segment, a range of host IDs for each unique subnet. An organization with a single network address can have a subnet address for each individual physical network. It's important to remember that each subnet is still part of the shared network address, but it also has an additional identifier denoting its individual subnetwork number. This identifier is called a subnet address. For example, consider a hotel or office building. Say a hotel has 1,000 rooms with 75 rooms to a floor. You start at the first room on the first floor and number it 1. When you get to the first room on the second floor, you number it 76, and you would keep going until you reach room 1000. I think that's 1000. Now, someone looking at room 521 would have a guess approximately which floor the room was on. If you were to subnet the hotel, you would identify the first room on the first floor with the number 101. 1 equals first floor, 1 and 01 equal room 1. The first room on the second floor with 201 and so on. The guest looking for room 521 would go to the 5th floor and look for room 21. Subnetting solves several addressing problems. First, if an organization has several physical networks but only one IP network address, it can handle the situation by creating subnets. Next, because subnetting allows many physical networks to be grouped together, fewer entries in a routing table are required, notably reducing network overhead. Finally, these things combine to collectively yield greatly enhanced network efficiency. Next, you will see how you can benefit from the features of subnetting in your network, how to hide information. One benefit of subnetting is the ability to hide your address scheme from the outside world. Supposing that the internet refers to Widget Inc. only by its single network address 130.57.suppose, as well as that Widget Inc. has several divisions and each is an independent business unit. Because Widget's network administrators have implemented subnetting, the Widget routers use the subnet address to route the packets to the correct internal subnet when packets come into its network. Thus, the complexity of Widget Inc.'s network can be hidden from the rest of the internet. This is called information hiding. Routers on the internet see only one external address for the Widget network. Information hiding also benefits the routers inside the Widget network. Without subnets, each Widget router would need to know the address of each machine on the entire Widget network, causing additional overhead and poor routing performance. The subnet scheme eliminates the need for each router to know about every machine on the entire Widget network. Their routers need only the following two types of information: the address of the subnets to which they are attached, the other subnet addresses. So, how to implement subnetting? Subnetting is implemented by assigning a subnet address to each machine on a given physical network. For example, in figure 1.14, each machine on subnet 1 has a subnet address of 1. The network portion of an IP address can't be altered. Every machine on a particular network must share the same network address. In figure 114, you can see that all Widgets Inc.'s machine have a network address of 130.57. That principle is constant. In subnetting, it's the host address that's manipulated. The network address doesn't change. The subnet address scheme takes a part of the host address and recycles it as a subnet address. Bit positions are stolen from the host address to be used for the subnet identifier. Figure 1.15 shows how an IP address can be given a subnet address. You can see here, because the Widget Inc. network is a class B, the first 2 bytes specify the network address and are shared by all machines on the network, regardless of their particular subnet. Here, every machine's address on the subnet must have its third byte read 00000001. The fourth byte, the host address, is the unique number that identifies the actual host within that subnet. Figure 116 illustrates how a network address and the subnet address can be used together. You can see here how to use subnet masks. For the subnet address scheme to work, every machine on the network must know which part of the host address will be used as the subnet address. This is accomplished by assigning each machine a subnet mask. The network administrator creates a 32-bit subnet mask comprising ones and zeros. The ones in the subnet mask represent the positions that refer to the network or subnet addresses. The zeros represent the positions that refer to the host part of the address. This combination is illustrated in figure 117. In our widget Inc. example, the first 2 bytes of the subnet mask are ones because widget's network address is a class B address formatted as network.network.node.node. The third byte, normally assigned as part of the host address, is now used to represent the subnet address. Hence, those bit positions are represented with ones in the subnet mask. The fourth byte is the only part in our example that represents the unique host address. The subnet mask can also be expressed using the decimal equivalent of the binary patterns. The binary pattern of 11111111 is the same as decimal 255 dot. Consequently, the subnet mask in our example can be denoted in 2 ways as shown in figure 118. Not all networks need to have subnets and therefore don't need to use subnet masks. In this case, they are either said to have a default subnet mask. This is basically the same as saying they don't have a subnet address. The default subnet masks for different classes of networks are shown in table.14. So class format default subnet mask. So A network.node.node.node 255.0.0.0. B network.node.node 255.0.0. C network node 255.255.255.0. Once the network administrator has created the subnet mask and assigned it to each machine, the IP software applies the subnet mask to the IP address to determine its subnet address. The word mask carries the implied meaning of lens. In this case, the IP software looks at the IP address through the lens of its subnet mask to see its subnet address. An illustration of an IP address being viewed through a subnet mask is shown in figure 119. In this example, the IP software learns through the subnet mask that instead of being part of the host address, the third byte of its IP address is now going to be used as a subnet address. The IP software then looks in its IP address at the bit positions that correspond to the mask, which are 00000001. The final step is for the subnet bit values to be matched up with the binary numbering convention and converted to decimal. In the widget Inc. example, the binary to decimal conversion is simple as illustrated in figure 1.20. By using the entire third byte of a class B address as the subnet address, it is easy to set and determine the subnet address. For example, if Widget Inc. wants to have a subnet 6, the third byte of all machines on that subnet will be 00000110, decimal 6 in binary. Using the entire third byte of a class B network address of the subnet allows for a fair number of available subnet addresses. One byte dedicated to the subnet provides 8-bit positions. Each position can either be a 1 or a 0, so the calculation is 28 or 256. Because you cannot use the 2 patterns of all zeros and all ones, you must subtract 2 for a total of 254. Thus, Widget Inc. can have up to 254 total subnetworks, each with up to 254 hosts. although the official IP specification limits the use of 0 as a subnet address. Some products actually permit their usage. Microsoft's TCP IP stack allow it, as does the software in most routers, provided you enable this feature. This gives you one additional subnet. However, you should not use a subnet of 0, all zeros, unless all the software on your network recognize this convention. How to calculate the number of subnets. The formula for calculating the maximum number of subnets and the maximum number of hosts per subnet are as follows. 2x number of masked bits in the subnet mask minus 2 equal maximum number of subnets. 2x number of unmasked bits in subnet mask minus 2 equal maximum number of hosts per subnet. In the formulas, masked referred to bit positions of 1 and unmasked refers to positions of 0. The downside of using an entire byte of a node address as your subnet address is that you reduce the possible number of node addresses on each subnet. As explained earlier, without a subnet, a Class B address has 65,534 unique combinations of ones and zeros that can be used for node addresses. If you use an entire byte of the node address for a subnet, then you then have only 1 byte for the host address, leaving only 254 possible host addresses. If any of your subnets will be populated with more than 254 machines, you have a problem. To solve it, you would then need to shorten the subnet mask, thereby lengthening the host address. This gives you more available host addresses on each subnet. A side effect of this solution is that it shrinks the number of possible subnets. Figure 121 shows an example of using a smaller subnet address. A company called Acme Inc. expects to need a maximum number of 14 subnets. In this case, Acme does not need to take an entire byte from the host address for the subnet address. To get its 14 different subnet addresses, it needs to snatch only 4 bits from the host address. 4 minus 2 equals 14. The host portion of the address has 12 unstable bits remaining. 212 minus 2 equals 94. Each of Acme's 14 subnets could then potentially have a total of 94 host addresses. 494 machines on each subnet should be plenty. Figure an example of a smaller subnet address. You can see here. Applying subnetting. Sometimes subnetting can be confusing. It can be quite difficult to remember all those numbers. You can step back a minute and take a look at the primary classes of networks and how to subnet each one. You start with a Class C because it uses only 8 bits of the node address, so it's the easiest to calculate. In the following sections, we'll look at how to subnet the various types of networks. Class C. If you recall, a Class C network uses the first 3 bytes, 24 bits, to define the network address. This leaves you 1 byte, 8 bits, with which to address hosts. So if you want to create subnets, your options are limited because of the small number of bits left available. If you break down your subnets into chunks smaller than the default Class C, then figuring out the subnet mask, network number, broadcast address, and router address can be kind of confusing. Table 1.5 summarizes how you can break a Class C network down into 1, 2, 4, and 8 smaller subnets with the subnet masks, network numbers, broadcast address, and router address. The first 0 bytes have simply been designated as .x, .y, .z. Note that the table assumes that you can use all 0 subnet too. So number of desired subnets, subnet mask, network number, router address, broadcast address, remaining number of IP addresses. So 1, 255.255.255.0, x.y.z.0, x.y.z.1, x.y.z.255.253, 2, 255.255.255.128, x.y.z.0, x.y.z.1, x.y.z.127, 125. 255.255.255.128, x.y.z.128, x.y.z.129, x.y.z.255, 125. 4, 255.255.255.192, x.y.z.0, x.y.z.1, x.y.z.63, 61. 255.255.255.192, x.y.z 64, x.y.z 65, x.y.z 127, 61. 255.255.255.192, x.y.z.128, x.y.z 129, x.y.z 191, 61. 255.255.255.192, x.y.z 192, x.y.z 193, x.y.z 255, 61. 8. 255.255.255.224, x.y.z.0, x.y.z.1, x.y.z.31, 29. Okay. 255.255.255.224, x.y.z.32, x.y.z.33, x.y.z.63, 29. 255.255.255.224, x.y.z.64, x.y.z.65, x.y.z.95, 29. 255.255.255.224, x.y.z.96, x.y.z.97, x.y.z.127, 29. 255.255.255, sorry, 255.255.255.224, x.y.z.128, x.y.z.129, x.y.z.159, 29. 255.255.255.224, x.y.z 192, x.y.z 193, x.y.z 223, 29. 255.255.255.224, x.y.z 224, x.y.z 255, x.y.z 255, 29. So I'm going to leave it here today for this live stream. I'll continue subnetting in the next one. So thank you for listening and have a nice evening.